All right.
Let's get started.
I like Parks and Rec. I can't help it.
Okay.
So real quick, I like Parks and Rec. A couple quick announcements. So first off, there was an issue where a lot of people were missing a point on that last problem on homework number 4. Maybe I missed it. I checked my solution. I didn't see anything wrong with the solution. So usually when I have a lot of people missing like one point, it's an indicator maybe I have something wrong as opposed to you all. So I checked, but I couldn't find anything. But if you see like something wrong on my homework 4 solution, please let me know. And if there's something wrong, I will make sure that you all don't get penalized for my mistake. But I really couldn't find anything. I looked. Now homework number 5, the T-beam and doubly reinforced beam assignment, that is due on Wednesday. So we are going to open up some time for questions here in a second. I've already had a couple, but it was very like minor, like you know, I don't want to say minor, but it was little numerical questions. Before I open that up, just remember that, remember it's due on Wednesday. I did have one other announcement I'd like to mention. We're having an event on Marshall's campus on Saturday at Science Olympiad. It's primarily for like high schoolers and middle schoolers and things like that. It's Saturday. It's on campus. If you're available, I could really use a couple student volunteers if you're around. That would be great. But we can talk about that as the date approaches. So yeah. Okay. All right. Homework 5. This is the last day that you have to turn it in. So it's, sorry, not the last day you have to turn it in. You're like, what? See, right here, my coffee hasn't kicked in. So, sorry. Now you're awake. No, sorry about that. What I meant was this is the last day you have to ask questions before you turn it in. Blech, sorry. I'll wake up. I'll get there. Are there any questions on homework number 5 before you submit it on Wednesday? I've already had a couple, so.
On the second problem, it's kind of like, I guess you can kind of see it here, it's like 2 elements together.
Yes.
How exactly should we handle that? I kind of did it one way, but I wasn't very confident with it.
That's a good question. So on problem, what number is it, 2?
Yeah.
2. The upside down U, the N. So basically what you have is a big flange and 2 webs. So what I would do is imagine those 2 webs are right in the middle. So your effective flange width is going to be taken as, what, 36 inches? Your H sub F is going to be 4, and then your B sub W is 10. But you don't need to determine B because it's the width. So just imagine you're making a cut right here and a cut right here, and just making a T-beam out of that. Because that's basically what this is. When you bend it, it's going to act like you have a big flange here and a web here. So does that make sense? So it is a T-beam just arranged a little oddly. So yeah, the whole area, both steel together. Does that make sense? You can do that. That would work. You'd get the same answer. Because here's the thing. If you were to take that beam and just stack it right next to, like take it and just copy it over, the capacity would just be doubled. So you can do that as long as you're properly having your values. In other words, like don't cut it in half but use 4 number 10s. Or don't cut it in half and use half of D. You can't do that. So you can cut it into half transversely though, and that's fine. So that should be fine, yeah. Nothing wrong with that. Any other, I mean, we got time. So. Okay. All right. With that, let's get into shear. Now I'm going to go ahead and tell you, shear's different. All right. And I mentioned that before. I I don't like beginning a topic by saying, guess what, this is the most difficult topic in the entire class. And I'm not saying that shear is difficult, but you kind of got to pay attention. And I would argue that if there's any topic that flexes your CE 312 muscles, this is the one. Because when it came to moment, all we were doing is saying WL squared over 8, and that's it. That was our analysis, WL squared over 8. But with, yep, I missed something. What?
312.
What? Structural analysis. If there's any, I need to pull the announcement slide up again. That picture of Ron Swanson starting to have some truth to it. No, if there's any topic that stretches your ability to perform structural analysis, it's this one. For beams, we just said WL squared over 8. I mean, I want you to think about that for a second. We would have a beam that was simply supported, and we did all this work to define the load, but we really didn't perform any pencil to paper structural analysis. We just used a little formula that told us what the maximum moment at the center of the beam was, and that was it. Well, this is where your structural analysis abilities are really going to be, shall I say, tested, okay? And that's in shear. Now, we went over behavior last time. We talked about, here's what a bending moment diagram looks like for the types of beams we've been designing so far. But here's the shear design, or the shear diagram. And so what we need to do is design and detail reinforcement according to shear. Now, what we're ultimately going to get is a reinforcement pattern that looks something like this. We're, basically placing those hoop stirrups along the span, and we're going to have more of them bunched up near the supports. Less of them near the midspan, but this is basically going to be how we're going about things. We talked about Moore's circle and how when you have a state of pure shear, that Moore's circle states that your worst case orientation is at a 45-degree angle, and that's why when you have a beam that's subjected to shear, that's why it cracks at a 45-degree angle, because it's opening in the direction that where it's experiencing a direct tensile stress. And remember, concrete is a material that behaves very poorly in tension, so that's the way it's going to open, is along the direction of tension. Now, as for capacity, the capacity is, first off, phi. Phi is constant. Phi is 0.75. There's never in shear, and actually, really from here on out, there's really never an instance where we have to determine phi. It's usually just given to us. So for shear, it's given. For deflections and development length later on, we don't even look at phi. And for columns, that's going to be a lookup. So it's going to be pretty straightforward. Phi is 0.75. And then how do we determine how strong a beam is? Well, it's the shear capacity provided by the concrete plus the shear capacity provided by the steel. So it's basically a sum of forces in the y direction. We have a shear load applied, and we have these two shear forces resisting. Now, the shear strength provided by the concrete is pretty easy. It's a pretty simple count. You've got to pay attention to your units. So when you just raw compute this out, put in PSI, get out PSI, you're actually going to compute a V sub C value in pounds, not kips. So just be aware of that. For the strength provided by the steel, it's the area times Fy times this term D over S. And D over S is basically telling us how many stirrups that we have that cross a given crack. Yes, sir?
I saw the slide for the concrete shear resistance. Will that always be given to us?
Well, you really have to calculate it. Lambda is the same parameter as it was before. Remember, it's 1 for normal weight concrete, it's 0.85 for sand lightweight concrete, and 0.75 for lightweight. So it's not really anything you calculate. It's something that you'll have to determine. I'll say this though. The only thing that would make this complicated is I don't know, there's really no complication. Just make sure that you remember what those values are from the F sub R calc, and it's the same. And unless otherwise noted, we're going to go with normal weight concrete, so lambda is going to be 1 anyways. So, sound good? Now, V sub S, this is the area times Fy times D over S. So that D over S, basically we're assuming that the crack crosses, it's a 45-degree region. So we're basically saying that crack is D wide and D tall. And so D over S is basically saying, well, how many stirrups cross a given crack? And that'll tell us where we're getting our shear capacity. So that ratio multiplied by AVFY will tell us how much shear capacity we're getting out of the steel. As for AV, just be very careful what area you're using. It is very, very common for us to use number 3 stirrups. It's very common for your stirrups to be a lot smaller than your main reinforcing steel. We've been doing beam design, and we'll use things like number 8s or number 9s or number 10s or something for the tensile steel. But for the stirrups, it's very common to use like number 3s or number 4s. So if I say that they're number 3 stirrups, be very careful. That doesn't mean that the area is 0.11. It depends on the stirrup configuration. So if we had a stirrup configuration that looked like this, if here's my cracked region, to fail that steel, I not only have to rip through one bar, I basically have to rip through 2, because that crack is going to go through 2 stirrups. So the AV value that we would use would be 2 times the area of the bar. So this would be some other examples. So these 2 over here on the left are additional examples where we would have 2 bar areas would help us determine AV. For the third one, this I-beam looking cross-section, our AV would not be 2 times the bar area. It would be what? 1 times the bar area. And then for what we have here on the very, very right, this would be something more like a column cross-section. We wouldn't be looking at 1 or 2. We would be looking at 4. Okay. So the easiest way to determine is just samurai sword or lightsaber right through the middle of it and ask how many bars are you cutting through. So it's one thing you might hear me mention in a lot of problems is I'll say something like a U-shaped stirrup. And so a U-shaped stirrup is going to be shaped, like a U. So a U-shaped stirrup would be a very indicative of 2, or it would be not very indicative, it would be indicative of 2 bar areas. Sound good? Okay. All right. Now, let me very slowly walk you through a lot of this. Just so you're aware, ultimately what we're after in shear is a shear design. I have one problem on my shear homework assignment where I'm asking you to analyze a shear capacity, but to be honest, that it's a pretty simple problem. I mean, if I just give you a beam, I really don't think there's much academic value in saying, okay, compute VC, compute VS, add them together, multiply by 0.75. I don't really think there's much academic value beyond doing that problem once, just so you see where the equations are coming from. What I'm really after is design. Okay? The reason why I'm so I'm so focused on design is because very, very, very rarely in the world of reinforced concrete design are we analyzing for shear. Usually we kind of think of shear from the designer's standpoint. We kind of think of shear as an afterthought. We have a beam. We start tinkering around with how wide the beam needs to be, how deep it needs to be, what the area of steel needs to be, such that we meet moment demand. Okay, now we got a beam. Then we have to take that beam and reinforce it according to shear. So shear design is something we do at the end once the beam design has already been, the flexural design has already been completed. So we rarely need to analyze for shear, except if you're in like a rating environment. But in the end, again, that's why that first problem's there is pretty simple. Now, the code lists some requirements according to shear, things like what's the minimum area of steel, what's the maximum stirrup spacing. Like I said, our goal is design when we're talking about shear. And so what I am going to do is I'm going to rearrange a lot of these limits, and instead of trying to determine what's the minimum AV, I'm going to try and determine what's a feasible maximum stirrup spacing, because that'll guide me in terms of design. So all of these limits will sort of be rearranged in order to solve for S. You don't really have to do that below, but I would have for the one up top. Okay? So, excuse me. Now, what I'm going to do here is I'm going to go through an analysis example. I don't really think there's much academic value beyond what we're doing here. However, there is something that is of academic value with this example, and we're going to start breaking out our CE312 muscles. Structural analysis. Now, I have an analysis example related to shear, but I'm doing this so that you all can kind of remember what's going on with the whole structural analysis aspect of it. So here I have a beam, and the beam has, let's see, 4 KSI concrete, 60 KSI steel. It's simply supported. It has a 24-foot long span. We have number 3 U-shaped stirrups. So everybody see what I mean by U-shaped. We have 1.5 kips per foot in dead load, 3 kips per foot in live load. But what I really want to look at is this. Okay? So just so you're aware, what we see here is a shear stirrup layout. Okay? Now what I've got here are 4 regions. Okay? Now these 4 regions are, we have region 1, region 2, region 3, region 4, and as we go away from the support, what we're seeing is that the stirrup spacing is increasing. Like here we have a stirrup spacing of 4 inches, here we have a spacing of 8 inches, here we have a spacing of 10 inches. Here we basically don't have any stirrups at all. And so these regions are going to help us determine whether or not this beam is performing adequately. Now, spoiler alert, I've kind of given you the answer, okay? And I want to show you how we're arriving at that answer very soon. Before that, though, let me get out of this real quick. That's a good, yeah, I'm glad you're here. Let me go ahead and mention that now. So this is the beam. Now this beam is what, 24 foot long? So what you're seeing here is like half of the beam. So the beam here starts here and it's 24 foot long. So this is the reinforcement pattern from 0 to 12 feet. And then imagine I took this and mirrored it. That would be the reinforcement on the other end. So if your loading and your geometry is symmetric, which is very, very common in structural design, what we do when we're speccing out stirrups is we will only spec out from the support to midspan. And then we just say, well, that's just going to be repeated along the other end. Does that make sense? Okay. All right. So this is going to be rather quick. Okay, so the first thing I'm going to do is I'm going to compute the concrete capacity. Now, in order to do that, let me take a look at the actual beam. This is going to be big. Forgive me. Oh, I knew that was going to happen. Okay. Now we have an FC prime that's 4 KSI, and we have a lambda that's 1, because for this beam we're looking at normal weight concrete. Okay? Now we have a B that's 12 inches, and we have a D that's 24 inches. So when you're computing V sub C, it's 2 lambda BW D square root of FC prime. So that's 2 times 1 times 12 times 24 times the square root of 4 KSI, right? There we go. No. Dr. Mike, you're wrong. You're an idiot. There we go. Square root of 4,000 PSI. And so when you plug and chug this, what do you get? First off, the units. What's the answer going to be in? No. It's in pounds. You're taking PSI and you're multiplying it by inches and inches. So when I say answer, I should have said VC. What's VC going to be in? VC is pounds.
36,429.
Right? So that is 36.43 kips. What do you mean? I mean, it is, yeah. Yeah, but look, you have PSI times inches times inches. Yeah. All right, sound good? Okay. Now, here's what I'm going to do for the steel capacity. I'm lazy, so I'm only going to do this once. I'm going to do this for region 1. All right, and what do I mean by that? Here's the beam. Here's the beam, right? Okay. Now, in region 1, what is the stirrup spacing? 4 inches. Okay? We have a D value, bless you, of 24 inches. We have an FY. Now, we call this FYT, just so you're aware, if the reason for the notation is that's FY of your transverse reinforcement. So longitudinal along the beam, transverse going up and down, although it's still 60 KSI. And now we have to look at AV. Okay. Now, first off, how many bars are we going to consider? Say it again? No, for AV. No. Hold on. Guys. How many bars are we going to consider? Now, you're about to, I mean, help me. If there's a question, like, let me know. We're talking about just a single bar. Remember, hold on. Remember the way that the math works. Okay? Here's the equation that we're going to use. We're taking the area of a single stirrup times Fy times the number of stirrups across a given crack. So we're going to account for the number of stirrups. What I'm asking is, if I have a single bar, how many sections do I have to fail through across a given crack? And for here, it's 1, 2. Everybody with me? All right, let me know if you're not, because, I mean, we had like 2, 2, 1, 4, and then 26. So, let me know. Everybody okay with this? All right, so again, we're just looking at a single bar now. We're going to take into account the number of bars here soon. Everybody with me? Okay, all right. So, do you agree then that the area in shear is going to be 2 times the area of the bar, right? Now, what's the bar? What is the size of the stirrup on this problem? Anybody remember? Number 3. Okay? Does everybody see that? They're number 3 stirrups. Okay? What is the area of a number 3 bar? Okay? So that is 2 times 0.11 square inches. Now, before we move on, there are a couple of places that you could find that out. Let's say you don't remember what the area of a number 3 bar is. Well, first off, it's on slide 187. These are the standard bars, and these are their areas. So all the areas are listed there if you don't remember. Okay? But let's say you don't have that. Well, let's go back to this. Remember this? Well, look at the first row. The first row is the area of a single bar. So, all that right here. So, ultimately, what we're going to be doing is taking 2 times 0.11 square inches. That's the area of a single bar, or 0.22 square inches. Is everybody okay with that? Now, what we're going to do to compute VS is we're going to take AV times FY times D over S. Now let's pay attention to that calculation very closely. So this is 0.22 square inches. KSI. And then this is 24 inches divided by 4 inches. So let's pay attention to this fraction. What is 24 over 4? 6. Okay, so here's the beam, okay? And so if we're talking about region 1 and we're talking about it cracking under shear, what we're saying is that it's going to crack something like this. And what we're saying is that across a given crack, we have 1, 2, 3, 4, 5, 6 bars that we're going to fail through. Does everybody see that? And that's how we're accounting for that. That's how we're accounting for that spacing. Okay, so it's not 26 bars because the crack occurs like this. It's how many bars cross a crack. So we take the area of a single shear stirrup and we say, well, how many stirrups across a crack? So that's why we do 0.22 times 60 times 6. Okay, does that make sense? Everybody okay with that? Now, what does this come out to be? 79.2 what? Kips. All right. So now can we combine that with our previous calculation? Like we had VC in kips, we had VS in kips, so tell me what to do. Add them up and you'll get VM, but what should I do once I add them up? Say it again. There you go. So why don't I do this? Why don't I say design capacity and I'll say that my V or phi VN is just phi times VC plus VS. Just do it all at once because I'm lazy. All right. So 0.75 times, what was that, 36.43? I'm sorry. Plus 79.2 kips. And so what does that come out to be? Do I have a second on that? Okay, all right. So let's pay attention to what we've got going on here, okay? What have we computed? We've computed phi VN. This is the factored shear capacity, right? Now, I would argue that this value is only going to be valid in the region that S equals 4 inches, right? Where does S equal 4 inches? Well, it equals, so let's think of this like it was a graph, okay? So let's do this. So this right here is X equals 0, right? This right here is X equals, we'll say 144. We'll do it in inches. So this 86.72, where is it valid? It's valid from X equals 0 to X equals what? 52. All right? And then this is going to, so what we would have to do is we'd have to do all of that again, okay? However, we would do it, so what would change from doing it from this region to this region? What would change? The S would go from 4 inches to 8 inches, right? So we'd change that to 8. We'd compute another VS, compute another phi VN. Everybody with me on that? Then, what's that? Well, it was, but we converted it, remember? Like when you initially calculate it, you get 36,429 pounds, but 36,000, yeah, so. Everybody okay with that? So we would then have another plot. So you're saying that the only difference in region 2 is we would have a different S value, right? That S value would change, so that would change VS and VVN. And that would go from x equals 52 to x equals what? Say it again. There you go. And then we'd have region 3 that would go from x equals 84 to x equals what, 124? Now what about this region 4? How would we determine the capacity? Well, I'd argue there's no stirrups in region 4 at all. So what is the capacity? No. The VC, exactly. So it's the shear. Remember, how do you determine the capacity? It's the shear capacity provided by the concrete plus the shear capacity provided by the steel. And I would argue that in region 4 there is no steel. So well, hold on. I'm going to get to that here in a sec. So here's what I would propose. Okay, I would propose that in this region here, VVN is 86.72. So can somebody do a quick count? Tell me, what would it be in right here? Like, how would you do that? And what is that?
27.32.
Say it again.
27.32.
Sound good? Okay, now, what was your question?
I was just going to say, don't we, when we do design beams, we only care about the maximum shear, so when we do every single section?
Nope. That's what makes shear different, is because we are laying out our stirrups according to the demand. If we went with what you said, we would just use the same stirrup spacing across the board, okay? In other words, we would just use, let's say, 4 inches and just use them everywhere. What I'm saying is that now things are a little different. See, if we're talking about, let's say, region 2 isn't seeing as much shear as region 1, so we can back that off, and back that off. So that's where shear gets different, is you're saying, well, don't we care about the maximum? Not with shear. With shear, we want everything. That's where I was saying you got to flex the structural analysis muscles a bit, because we're actually going to account for how the shear changes across the beam. We don't typically do that with moment, but we'll talk about why here in a little. That's later. So, although we can if the moment demand gets really crazy, we can. Everybody with me so far? So let me ask you a question. Do we need to do this, or are you all okay with me not doing these? I'm asking. Yes, that's what I'm asking. Do you know how to calculate these? Like, do I need to walk through it? Exactly. Everybody okay with me skipping that? Okay. Now what I want to do is I want to pull up this. Okay? So here's the example. Here's the stirrup layout. I want to look at that. Let's take a look at this plot. What I want to do right now is I want to pay attention to the red line. Okay? How many different stair steps do you see on this red line? Well, I mean, I see 4 landings. Like 1. Hold on. Oh, don't do this to me. I see 1, 2, 3, 4. Okay? What do you think this x value is right here? Maybe it's x equals 52 inches. Maybe this is x equals 0 inches. And I don't know, maybe this capacity looks like 86.72. Is everybody seeing where this is coming from? And then as we get away from the support, the shear capacity is going down to a value of, what did you say this was? And that's from x equals 124 inches to right here, That's where X is 144. This,
Continuing on, that's just symmetry. Is everybody okay with that?
now, okay, so
What?
did I do something incorrect? Well, hold on. What was the original value?
The original value was 36.
I think there might be a fee forgotten on this. Huh. We're going to count this as 0.4 mistakes. 0.4. I'll give you 0.4 on this one. This one's good. Yeah.
So what is the blue line? Is that
That's a great question. Let's talk about that blue line. No, don't spoil it. Don't spoil it. Don't spoil it. I got questions to ask about that. Let's talk about that blue line. Let's talk about that blue line. Oh, we were going to talk about it anyways. You don't have to blame him. Now, let's go back to the fundamental basis of LRFD. We have on one side the resistance, the strength of the section. What's the other side? There's the strength, how much it can hold up, but what's the other end of the equation? Thank you. How much we're putting on it, right? The loads. So let's do some structural analysis. I'll come up with another question. Now, how long was this beam? No. No. Let's keep everything consistent. I'm going to use feet, and you'll see why here in a second. So how long is the beam? What is the dead load? Does that include the self-weight? Or does it say? We're going to assume it does. Bless you. What's the live load? So tell me what to do. Six point six. Okay? Now, so let's go back. I need your help in going back to CE 312 structural analysis land. What you're telling me is that I have a beam that has a load on it that's 6.6 kips per foot. We're going to get real here, okay, as opposed to getting virtual. So we have a 6.6 kip per foot load on a beam that's 24 feet long. So I propose that there's an AY, and I propose that there's a BY. And then this is 24 feet long. Somebody tell me how to find those reactions. We can. Well, hold on. So let's go back to what he said. I'm going to entertain what you said. So collapse that into a single point load, some moments at A to determine the reaction at B, some forces at B to determine the reaction at A. What were you saying? So that's collapse it into a single point load. We're not going to do that. We're not going to do that. You're on to something, but we're not doing that right now. Why did you say that?
It's symmetrical on
exactly right. Half and half, right? So collapse, let's do that. Collapse that into a single point load, and what do you get? I have a second on that? So how would I get those reactions again? And what is that? Right? Now, tell me what to do. I'm not saying anything. You're going to tell me what to do. I know you know how to do this. There we go. All right, all right. So we start at 0. Start at 0. Go up. 79.2. Then what? So we, all right. So we go down to negative 79.2, and we go, boo, right? And the technical term for that, for the folks watching the video, is we drop down linearly, right? To negative 79.2. And this is 0. And the slope of that line is negative 6.6, right? So what is this dimension from there? Like, what's this dimension? Okay. So here's what I'm asking. Let's take a look. This is a line, right? Give me 2 points on that line. Okay. 12, 0. Can you find the equation of a line? You're looking at me like I'm... okay, hold on. Hold on. Can you find the equation of a line? Here's what's going to happen. I'm just going to sit in this chair until somebody tells me what the equation of that line is. Guys, the equation of a line. Come on. Do it. Come on. I'm getting worried here. You're like laughing, but everybody's like, wait, how do I do this? Like no, come on. Now, what you're on to something. I'm hearing you saying it. Go ahead. Thank you. Oh, it was right there. The slope of this line is negative 6.6. This is the y-intercept. So the equation of this line yes, glad somebody said that. Just making sure everybody's awake. And I got somebody paying attention. Is everybody with me on that? Everybody, okay. Now, there we go. You asked what the blue line was. Here's the blue line. Although, I'm going to be honest. Hold on. What was the reaction? 79.2? I've got something off on this graph because it's not right. Something's off. You know what? Let's just do this for real. What did we say the equation of the line was? All right. Okay. So that's looking right because that's x equals 0, or x equals 12, and that's equals 0. So let's plot this. Insert, plot. Okay. So far, so good, right? Now, what were the stair-step values we had? What was that? 86.72 and so on and so forth. Everybody starting to see where this is coming from? Okay. Now, here's the big point. We're running out of time, and I don't have time to redo everything. But let me ask you this. Does everybody see how the stair-step is a little bit above the blue line? What do you think that means? We're good. Why? Bam. Exactly right. The capacity is larger than the applied load. So that's what we're after. Okay? Now, what he said was, well, why don't we just use the worst-case design and do that everywhere? That's a possibility, but ultimately what that would mean is you'd have a beam that's way over-designed. Okay? So ultimately what we're going to need to do, and we'll start this next time, is we'll need to figure out, well, how exactly do we lay out a stirrup pattern according to Shear? Okay? Now, there's a process. We're going to go through this process step by step next time, and don't worry, there's a nice little step-by-step procedure. But I'm going to save that, getting into that for next time. There's a couple ACI code provisions that we kind of need to discuss. Yes?
Is there a reason that when
What? I don't...
the capacity gets to be a lot more than the load?
Oh, that's a great question. This right here, how, you can see how this is accurate, but this right here really isn't. That's a great question. There's a couple of reasons for that, and that'll become very, very clear next time, but I'll give you two answers. One, even if I provided no stirrups, there is still the capacity provided by the concrete, right? So there is a point where it's just going to go on forever. And we don't really have much room to change the size of the beam because remember, the beam size was figured out because of all the moment. So there's that. Point two, and this will become a little more clear next time, but there are limits as to how far we can push the envelope with shear. There are certain regions where the code says, I don't care how much load is on the beam, you're still putting this many stirrups. And the reason why is because when beams fail in shear, they go quick. So the code has some safety provisions, if you will, to back that off a bit. But that'll become clear next time. I don't want to dig too heavily into the details. But I am going to look at that graph because there's some numbers that look a little weird. But I'll check that next time. Everybody good? See you in a few minutes.